In this video, I'm gonna go over collision in one dimension. I will define collision, I will tell you how many types of collisions do we have, and how to solve problems using conservation rules. What is collision? In physics, every interaction between two or more bodies resulting in momentum exchange is called collision. Like a couple of toy cars, when they collide, they have a very short touch and then they have momentum exchange. Let's say the car number one has a velocity of v1 rightward, and let's say car number two is at rest. After the collision, car number two also will have a momentum. So necessarily a momentum exchange happened. But it's a big mistake if you think that necessarily collision will have a touch. No, sometimes it's touchless. Like in this case, in this experiment, I put a couple of bar magnets on wheels. I will push or move the magnet number one at a speed or velocity of v1, and before the cart number one can get and touch car number two, due to the repulsion between north poles, cart number two is moving and is receiving a momentum. So this momentum exchange is a kind of touchless one. In universe, we have billions of galaxies. They are in gravitational interaction. And this kind of interaction is actually touchless. And it is also regarded as a collision. So collision in general is momentum exchange. Different types of collision and how to use conservation rules for each one. First of all, a very basic one is elastic collision. In elastic collisions, before the collision, two objects, at least one of the two objects will move. The other one may be at rest or may move. It's not a necessity, but one of them at least must be in motion. After the collision, it's very important. They separate, and more than that, there is no energy loss or energy gain. This is called elastic collision. So, elastic collision, first of all, must have no energy loss or no energy gain. And after the collision, two objects will separate. Conservation rules. Conservation of momentum is always valid in all collisions. But conservation of kinetic energy also is valid here. So I can say before the collision, the total momentum of the system is equal to the total momentum of the system after the collision. More than that, the total kinetic energy of the system before and the total kinetic energy after will be equal. But the second one is inelastic collision. In inelastic collision, before the collision, objects are separated. At least one of them must move. After the collision, they get separated, but it's a very important condition here. We must have energy loss. If we have energy loss, we can still use conservation of momentum, but conservation of kinetic energy is violated. We cannot use. So in this case, we can say just momentum, the total momentum of the system before the collision is equal to the total momentum of the system after the collision. That's all, nothing more. A very specific type of inelastic collision is perfectly inelastic one, in which before the collision objects are separated, they touch but they stick to each other, and so they combine. After the collision, they will have one common velocity. Here, still we can use conservation of momentum, but conservation of kinetic energy is violated. Of course, here, as it is a kind of inelastic collision, we necessarily will have a violation of kinetic energy and energy loss. But the very important condition for perfectly inelastic is combining the object, or the objects will stick to each other. The last one is superelastic. Superelastic is the one in which before the collision, two or more than two objects are combined and make a unibody object, and after the collision they get separated, like explosion. In this case also, energy is not kinetic energy is not conserved, and so we can still use the conservation of momentum, but conservation of kinetic energy is violated. But it's very interesting that before the collision, in this case, we have a kinetic energy of ek1, and after the collision, the total kinetic energy of the system may be something like ek2. Here ek2 is larger than ek1 because energy is gained. But in perfectly inelastic or in inelastic collision, the total kinetic energy after is smaller than the total kinetic energy before. It's very important. So, in short, I can say conservation of momentum is valid in all collisions, but conservation of kinetic energy is just valid in elastic case. The other ones will violate conservation of kinetic energy and we cannot use that. Here I have a couple of cards with same masses and I consider the collision to be fully elastic. Okay? Here I consider the second card to be at rest. Card number 2 is stationary, initially at rest, but card number 1 is moving at a velocity of v1 rightward. Guess what happens if they collide? You see, card number 1 will stop and card number 2 will move to the same direction, the same velocity. v2 is equal to v1. The reason, this is elastic collision. So P1, the total momentum before, is equal to P2, the total momentum after. M times V1 is equal to M times V2. Of course, masses are equal, so we can get rid of these two. We will have V2 is equal to V1. If you use conservation of kinetic energy, you will get the same result. Let's have a couple of masses with different size. The second card is the larger mass, but stationary. The first card is moving at a speed of v1, velocity of v1 rightward. Guess what happens if they collide? You see? After the collision, the smaller one will go back, but the larger one will go to the right, to the same direction as the smaller one had before the collision. The other is when the second object at rest is the smaller one and the larger one is moving to the right. Look what happens after the collision. You see? The larger one slows down, but it's moving to the right, but the smaller one will continue to the right at higher speed. Perfectly inelastic collision. When I say perfectly inelastic, I mean two objects will stick to each other, and so they will unify and make a unibody object. Necessary energy is lost. So when they collide, they stick to each other and they continue like that. Here you cannot use conservation of kinetic energy, but conservation of momentum is always valid. I will consider them one by one. Let's consider elastic collision. Here I have two different masses. Before the collision, they have velocities like v1 and v2. This is my supposition. And after they collide, as they have momentum exchange, it will be v prime 1 and the other v prime 2. We have two valid conservations, momentum and kinetic energy. Conservation of momentum means mv1, momentum of the first, and capital M times v2, momentum of the second, totally will be equal to the total momentum after the collision. Here be very, very careful, as momentum is a vector quantity. For example, if v2 is to the left, this is gonna be negative, okay? If one of them is to the left, as I suppose that positive direction is to the right, the left directed or pointed one will be the negative term. It's very important. Anyway, if I have suppose that both are to the right, they have positive signs here. After the collision, I don't know what happens. In general, I use positive sign for both, but if you solve this equation and find, for example, v prime 2, for example, negative 4 for instance, negative 4 meter per second, this negative sign means that v prime 2 is to the left. You can use also the conservation of kinetic energy here because it's elastic collision. So the total momentum of the first plus the total momentum of the second will be equal to the total momentum of the system after the collision. Here, as you see, term by term, I should use mass and velocity in kinetic energy, one by one. Of course, the last equation, as all terms are positive, there and negative sign has no effect. What if this is considered as inelastic collision? Let's say instead of elastic, I say it is inelastic. What happens? Nothing. I will have just one equation. The second one is violated. In general, you know that if it is elastic, I have a couple of equations as a system of equations, and basically I can have maximum of two unknown variables. But if this is elastic one, mathematically, as I don't have the second equation, in principle, I can't have more than one unknown variable. Okay, otherwise, I cannot solve this equation for two variables, v prime 1 and v prime 2. Both are not going to be outcome of just a single equation. But advantage of elastic collision is that you have two equations, and if you solve them, in principle, you can have two unknown variables and you can find them. Now let's consider superelastic collision. I have a couple of objects with different masses in general. They are at rest, but the connection is a spring. And I can compress this spring before interaction and save a potential energy, elastic potential energy in that. Then I release the system. When I release the system, although previously we didn't have any velocities for none of them, but here I have a velocity for m1 and a velocity for m2. Necessarily, of course, you know that they are in opposite directions. But it's very interesting that the total kinetic energy here is not zero. But previously we had zero kinetic energy. This is why in superelastic collision, again, conservation of kinetic energy is violated. But as we can always use conservation of momentum, we can say the total momentum before and the total momentum after are equal. How can we use that? Like this. Before interaction, none of the objects had any velocity. So the total momentum of the system is zero. After the collision, the total momentum of the system will be m1 v prime 1 plus m2 v prime 2. We put them equal to zero. Why? Because the total momentum after is equal to the total momentum before. Conservation of momentum. The total momentum before is zero, so the total momentum after is also zero. Anyway, we can take m2 v prime 2 to the right side of the equation and then solve it like that, make a ratio. V prime 2 over v prime 1 is negative m1 over m2. Here we have inverse relation. So if one of the objects has larger mass, it will have a smaller speed. Why I have a negative sign here? This is normally a mathematical result of this equation. Means that after the collision or after the interaction in superelastic collision, we expect opposite directions for the two velocities. Again here, as I mentioned, just conservation of momentum is used. Let's solve a problem. Stone A of mass 0.5 kilogram traveling at 3.8 meter per second across the surface of a frozen pond collides with a stationary stone B of mass 3. Also, let's say this is a stationary, VB is equal to 0, and VA is gonna be 3.8 meter per second. Mass of both objects also are given. Anyway, stone B moves off at a speed of 0.65 meter per second. So I know that this is 0.65 meter per second after collision. I don't know anything about the object A. So here just I know that I should find final velocity of stone A. Here also they mentioned that it's the same direction as stone A. So the velocity of B is rightward if I assume that velocity of A before the collision is to the right. Anyway, I don't see any evidence here that this collision is conserving kinetic energy. Is it elastic or inelastic? So I cannot use conservation of kinetic energy. But as always I'm allowed to use conservation of momentum, I can say total momentum before and after will be equal. Okay? So total momentum. So momentum before and momentum after are the same. Momentum before the collision will be m1 v1 for A, m2 v2 for B. But B initially is at rest, so this is gonna be 0. m1 v prime 1 is the mass of object A, and v prime 1 is my goal, the velocity of stone A. m2 v prime 2 is something I know because m2 is the mass of object B, and v2, as I mentioned, is 0.65 meter per second. So let's plug in the values. As I told you, this is 0 because the object B is initially at rest. Here I have mass of object A times the velocity, 3.8. Here I have mass of object A. I'm looking for v prime 1. 3 is the mass of object B, and this is the final velocity of object B rightward, so it's positive. Then I can solve this equation and find v prime 1 to be negative 0.1 meter per second. Negative sign means that object A is moving leftward, so it's negative 0.1 meter per second. So before the collision in this question, I have a speed of 3.8 meter per second for A. B is at rest initially, and finally A is moving to the left with a velocity of negative 0.1 meter per second. B also is moving to the right, 0.65 meter per second. Another question. For the railway tracks below, let's consider the railway tracks. Here I have a railway track of the mass of 6,000 kilogram, and the other is a smaller half of this mass, 3,000 kilogram. Initially, the lighter one is at rest, but let's say this is A. A is moving at a velocity of 2.5 meter per second to the right. After the collision, I don't know what will happen to A, and I will be looking for V, but the object B is moving to the right at a speed of 1.9 meter per second. Part A, the velocity of the first track immediately after the collision. Okay, so I'm looking for this, the velocity of cart A immediately after the collision. Okay, do you see any evidence that we can use conservation of kinetic energy? Do you see that the question mentioned it is elastic collision? I don't see any. So forget about using conservation of kinetic energy. I can use just conservation of momentum. So the total momentum before is equal to the total momentum after. M1 V1 is this, mass of 6,000 for the cart A and the velocity of 2.5 meter per second. 0 is for the object B, for the cart B, which is initially at rest. After the collision, mass of the cart A is again 6,000. V prime 1 is my goal, I don't know. M2 is 3,000, the mass of the cart B, and V2 is given as 1.9 meter per second. So let's plug in the values and find the velocity of object A or heavier cart A after the collision. It's 1.6. Positive sign means that the heavier cart A, is still moving rightward. Part B, the loss in kinetic energy. It's interesting. This part is explicitly mentioning that kinetic energy conservation is violated. Anyway, the loss in kinetic energy as a result of the collision. What should I do? It's very easy. Loss in kinetic energy means that I should find delta EK. What do I mean? Delta EK is the EK after minus EK before. EK after means the total kinetic energy of the system after the collision, and here EK before, the total kinetic energy before the collision. Let's do it one by one. Total kinetic energy of the cart A is EK1, a half of mv squared. This v is the initial velocity of the cart A. It's 18,750 joules. EK2, the kinetic energy of the cart B before, is 0. So let's say EK1 is gonna be just 18,750. Nothing more because the other is 0. After the collision, actually I have two kinetic energies for the cart A and for the cart B. In previous page, I found the velocity of object A to be 1.6, so it's 1.6 meter per second. You see that here, and 1.9 is given. Anyway, after calculation, it will be 12,623 joules, the total kinetic energy of the system after the collision. Anyway, it's smaller than EK1, so changing kinetic energy will be the final kinetic energy minus initial kinetic energy. And the answer is going to be 6,127 joules. This is the kinetic energy loss as a consequence of inelastic collision. Another question. A rail truck of mass 4,500 kilogram moving at a speed of 1.8 meter per second collides with a stationary truck of mass 1,500 kilogram. So before the collision, the second cart is at rest. It is at rest, initially at rest. First one is moving at a velocity of 1.8 meter per second. Let's say to the right. The two trucks couple together, they stick together. It is perfectly inelastic collision. So conservation of momentum is the only thing I can use. Calculate the speed of the trucks. Trucks means that they have a common speed immediately after the collision. Okay, after the collision, let's say the total mass is m plus m, but we have just a single velocity for the system. Here I can use this equation. Why? Because I have a total momentum before to be m times v1 plus 0 because it's at rest. Total momentum after is p2. So it's m plus m times v prime. I put them equal due to the conservation of momentum. So mv1 is equal to m plus m v prime. This is why I can say v prime is m divided by the total mass times v1. Let's use this equation and I plug in the values. 4,500 is the mass of the truck A, the first one, and this is the total mass at denominator. It's multiplied by v1, the initial velocity of the first truck. Anyway, the answer will be 1.4 meter per second. This is the common velocity of the system after the collision. Another question. Railway truck A, you see railway truck A here, moves along a horizontal track and collides with a stationary truck B. So before the collision, truck B is at rest. Let's say the truck B is at rest. So VB initially is 0. The two join together. Oh, join together means that this is perfectly inelastic collision. So I will have a common velocity of V after the collision. Immediately before the collision, Truck A has a speed of this. Okay, it's written here. Immediately after the collision, the speed of the trucks is v, as you see here. Okay, the mass of the truck A is given to be 1800. So the mass of A is 800 kilogram. Okay, and mass of the truck B is 1200. So mass of truck B is 1200 kg, kilogram. Okay, part AI, calculate V. Calculate V, I can just use conservation of momentum. No, I have no conservation of energy here. So let's say the total momentum before is ma times v1 plus 0, 0 because it is at rest, initially at rest. After the collision, ma plus mb, the total mass times the common velocity of the system. Okay, here I just plug in the values. 800 is the mass of A, 5 is the speed of A given, 2000 is the total mass. 2000 actually is 800 plus 1200. And V is going to be 2 meter per second. This is the velocity, the common velocity of the system after the collision. Part AI, calculate the total kinetic energy lost during the collision. Lost means that again you should find delta EK. Delta EK, which is gonna be EK2 of the system after the collision minus EK1, the total kinetic energy of the system before the collision. Anyway, the total kinetic energy before the collision is just the kinetic energy of the cart A. So I plug in the values and I find 10,000 joules. Then after the collision, they have a common velocity of V. I found it to be 2 meters per second. And here I have 2,000, the total mass of the system. Then I plug in the values and I have 4,000 joules. So the change in kinetic energy, the kinetic energy lost is this. This negative sign here is usually used for demonstrating energy loss. Anyway, if you don't put the negative sign here, just report 6,000 joules, it's evident that anyway the system has already lost kinetic energy because this is perfectly inelastic collision. And part B suggests where the lost kinetic energy has gone. Normally, I will have deformation or maybe conversion to internal energy and so forth. So it may have transferred into internal energy and sound energy. These are the usual procedures through which the system can lose kinetic energy. And that's all. It's done. Thank you for watching my video and thank you for being with me. See you soon.